All right, good morning and welcome to Office Hours. Hey there. I hope everyone's weekend is off to a good start. Probably for some of us, hasn't even begun yet. But yeah, I'm here. I'm ready. Sarajib, if you have any questions or anyone else who is, here live, I always prioritize um, live questions over ones submitted over email. So hit me up with any that you have. If not, I'm going to turn to my email. I know I was going through it this morning, and there are a few questions for office hours. So, in the absence of any live questions, I will get to those. But as of course, as always, I'll answer the live ones first. Ah. Okay, so Sarajit, all of the assignments in this class. So the question is, have I graded the prereq exams? All the assignments in this class are graded. Well, actually, I can't say that. So okay, so all of the exams in this class are auto graded by Canvas. Since there's no free response questions, you're given the grade that you earned instantaneously. That being said, if you're asking about, there was one problem where there was a typo in the prereq exam, and I have not been able to correct it because Canvas doesn't let you edit or alter an assignment that's live. And even though the prereq closed for the majority of the class already, in which case I'd be able to go in and change it, we had a few students who were late adds for whom the assignment was still open. So I haven't had an opportunity to correct it. If you're asking about that one, if you're asking if if you're asking about that question that needed a correction. Other than that, though, all the exams in this class give you your score upon completion of the exam. Does that answer your question? Solid. isotopes. That is correct. I have not yet graded the free response questions in lab. Let's see. Oops. All right, so the let's see. The question is, what element has the following electron configuration? And the electron configuration given has an argon core, and it's 4s2, 3d10, 4p4. All right. So the way you we're trying to find what element. What element has this electron configuration? So to answer this question, you have to turn to the periodic table, and just a quick refresher. So the first two columns of the periodic table, including helium, are the S block. All right, the other chunk of the main group, is the P block. The D block falls in between the S block and the P block, and then finally the F block is kind of floating down here. So you need to know these divisions of the periodic table. If you're going to assign electron configurations, it's the simplest way to do it. And so I definitely recommend knowing where your S, D, P, and F blocks are. Now, with that being said, the other thing we need to know is what these energy levels represent. So when we're told that this is, that we have a 4s orbital, that means we are on the 1, 2, 3, 4th period of the periodic table. And when you see that you have 2 electrons in the 4s orbital, that means, starting from the very end, that means you're going 1, 2 spaces in, right to the s block. Now, when you cross from the s block into the d block, as we're about to do now, the d energy level is always 1 lower than your s. And you can hit up lecture. I go into that there. If you want to see, again, I can totally do it now as well, but I'm keeping things brief in the interest of solving the problem. So we are moving into the 3D subshell, and we're going to go 10 spaces in. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3D 10. Now we're about to cross into the 4P subshell, right? The P block starts here. And one thing you'll notice is that the energy level for the S subshell and the P subshell are always the same, and they're always 1 higher. So you shift down to go to the D, and then you shift back up when you go from the D block to the P block. And we're told here that we're moving 4 spaces into the P block. So we go 1, 2, 3, 4. So when they ask us what element has this electron configuration, the answer is selenium. They most certainly do. Oh, let's see. All right, so let's look at the periodic table. So 3s2, yep, you count down. One, oops, let me open a new layer, there we go. 1, 2, 3. And then you move 2 spaces in, 1, 2. Magnesium is your dude. Magnesium would have neon, 3s2. Okay, great question. So let's talk about isotopes. Isotope is a relationship. All right, it's a relationship between two atoms. And what an isotope is they are atoms with the same number of protons but different numbers of neutrons. All right, so two isotopes will have the same number of protons. In other words, they're the same element, right? Having the same number of protons makes them the same element, but they have different neutron counts. I totally can. And what I'm going to do for this problem is I'm going to change the numbers. I'm going to alter the numbers slightly. So you can see the steps, the answers will be different, but I will totally walk through how to do this problem. So this is calculating the molecular weight. All right, so let's say that we have, all right, so here I'll write out a fresh problem. So let's say that 46 0.0% of dipium, which is not a real element, atoms, have a mass of 24.0 AMU and 54.00% have a mass of 27.40 AMU. What is, oops, sorry, the atomic mass? So let me actually correct this. This calculates the atomic mass. All right, now how are we going to do this? The way you, so we have been given the mass of two isotopes and their percent abundance, all right? The way you calculate the atomic mass, given the isotopic mass and the percent abundance, is you have to take what's known as a weighted percent. All right, you have to calculate a weighted average. Sorry, not a weighted percent, a weighted average. And the way you take a weighted average is the way you take a normal average is you add them all up, divide by the number of things. But that's assuming that every component of the mixture is represented equally. Here it's not. 46% has a lower mass, 54% has a higher mass. So we need to weight each mass accordingly. The way you do this is you need to multiply each atomic mass of each isotope by its percent abundance as a decimal, and then you add those together. So we need to, there we go, let me pause right there so I can grab this problem. All right, so we need to take our first atomic mass, which was 24.0 AMU, and we multiply this by the percent abundance as a decimal. And the way you convert a percentage to a decimal is you have to divide by 100. We're going to do the exact same thing with our second isotopic mass. We take that mass and multiply by its percent abundance as a decimal. And again, to convert a percentage to a decimal, you have to divide by 100. So we take these two products, and then we are going to add them together. But first, let's crunch our numbers. So we have, let's see here, 24.0 times 46 divided by 100. This is 11.04. When you look at sig figs, for this first number, 24.0 has 3 sig figs, 46.0 has 3. So our answer can only have 1, 2, 3 sig figs. I'm going to wait to round to the end, but I'm leaving these lines here to remind myself that I have 3 significant figures in this number. Next, let's take 27.40 times 54.00 divided by 100. This comes out to be 14.7, whoops, not 76, 796. When we look at significant digits for our second product, 27.40 has 4 sig figs, 54.00 has 4. So this product will have 4 sig figs. Again, I'm not rounding, but I'm leaving these 4 lines to remind myself that this number has 4 significant digits. Now that I've multiplied each isotopic mass by its percent abundance, I need to add these two together. So 14.796 plus 11.04 comes out to be 25.836. And now we have to apply the rules for sig figs. We have to look at precision, the last significant digit in each number. For 11.04, the last significant digit is in the first decimal place. For our second number, its last significant digit is in the second decimal place. So we're limited here by the least precise of these two numbers, which is 11.04. So we need to round to the first decimal place and 3 rounds down. So our final answer, given these numbers, is 25.8 and then AMU. Because every correct answer must have the correct value, correct number of sig figs, and the correct units. Ah, great question. So when you multiply 27.4, and you can actually see this right here. When you multiply 27.40, you've got 4 sig figs. 54.00 also has 4 sig figs. So the product of these 3 numbers, right, divided by 100, has 4 sig figs. So that individual product has 4 sig figs? No. The 100 is exact. So the 100 is exact. It does not influence your sig figs because this 100 right here, oops, this 100 right here is based on the definition of percentage. So it doesn't affect the sig figs at all. Multiplying 27.40 by 54.00 gives you an answer with 4 sig figs. 14.796. If we were to round this, it would round to 14.80. If you were to round it right there. Now, here's the deal. The reason why our answer has 3 sig figs is because of this number up here. All right. When you add 14.796 to 11.04, 11.04, because it is less precise, determines the precision of our answer. So that's why we end up with 3 sig figs. It has nothing to do with the 27.40 times 54.00. That product does have 4 sig figs. Our answer ends up with 3 because we're adding the product of 27.40 and 54.00 to our other product of percentage and isotopic mass, and that's what determines the precision of our answer. Um, sorry, what problem are you asking about? So what about protons and neutrons in general? I'm not sure I understand what you're asking specifically. Okay. Now I understand what you're asking. Okay, so to determine, well, okay. So here's the deal. And actually, we'll make use of our periodic table. So if you look on the periodic table, for example, let's look at iron. All right. The periodic table gives you what's known as the atomic number. Which is given the symbol Z, and Z is equal to the number of protons. All right, it tells you the number of protons that are in each element. However, the periodic table does not tell you how many neutrons are in an element, because that varies, right? There are isotopes, which are elements with the same proton count, right? But different neutron counts. So nowhere on the periodic table will you find the number of neutrons, and so therefore you can't calculate the total number of nucleons. That you have to be provided externally with something called the mass number. All right, the mass number is represented with the symbol A, and A is equal to the sum of the protons and the neutrons in the nucleus. All right, so it's number of protons plus number of neutrons. In other words, the atomic number is the total number of nucleons. You'll see this written, for example, like for iron. So if you have an element, the isotopic nomenclature will have the mass number superscripted and the atomic number subscripted. All right, and this is how it's depicted. So, for example, if you had an isotope of iron, 54. All right, this isotope of iron has 26 protons. And then to find the number of neutrons, we have to subtract the atomic number from the mass number. So we go 54 minus 26, which maybe I could do in my head, but I'm not going to try. Comes out to be 28. So this isotope of iron would have 26 protons, 28 neutrons, and the mass number A is the number of nucleons, which is just protons and neutrons together. All right, so I actually have to run. Office hours is up. I have to go take care of my 2-year-old. But Sarah, thank you for dropping by and making office hours interesting. And we'll be back here normal time this week, and for the rest of the summer session, pending, when the baby comes. But this week it'll be normal time, Wednesday 8 a.m.